Most of the forces we have encountered in physics have been constant forces. Things like friction along a surface, or the gravitational force mg, or even an applied force. But in this class, in AP Physics, we have encountered forces that do depend on time or that depend on position, like the spring force or the universal gravitational force. And here we will talk about forces that are dependent on an object's velocity. And this brings in the ideas of air resistance. The mathematics is a little bit more complex, which is why we have not discussed it until now. But we're going to see if we can battle our way through this sort of situation where we have forces that are resistant to an object's motion. You'll see how this force is defined with a negative sign, but they are dependent on the object's velocity. We will need to use some new calculus ideas. These formulas are written on your formula sheet, and the one that we're going to be using here is this one here. That the integral, when you have the function that you're trying to integrate, when it's in the denominator of a fraction, the integral ends up being the natural log of that function. And we are also going to use this sort of trick from our math class where e to the natural log of a function is equal to that function. So here we have a car of mass m, and it has a velocity right now of v sub 0. But a force starts acting against its motion, a resistive force, that has magnitude b times v, where v is the velocity of the object's motion. And we are going to derive an expression for the car's velocity. So first we'll think about which of these diagrams would represent the forces. We're going to be using F equals ma, and so we need to have a good idea of the force diagram. The vertical forces don't really matter too much in this situation. It would be the normal force up and the gravitational force down. But the key thing is that BV, B times V, would need to point against the motion, so it would point to the left. And there is no discussion about an applied force. It just says the object is moving. And so B would be the correct answer, the diagram in the middle. So now we could use Newton's second law to write an expression based on this force diagram. Our force is negative BV, again pointing against the object's motion, and I've turned this into a differential equation by putting a derivative in for the acceleration. And this is where the complexity comes through. When I want to solve a differential equation, what I need to do is to get the variables on opposite sides of the equation. So v is a variable and t is a variable. So I'm going to do a little algebra here and bring everything basically to the left except for the v's. So I've left all the dv is on the right, and I've divided by v to get all the v's together, and then everything else is with the t. This is just kind of a good technique with this style of problem. And then what we'll do is we'll integrate both sides of the equation. So just like you can square root both sides of an equation, you can integrate both sides. When we do that, the left-hand side is something we've seen before. It's just a polynomial. But the right-hand side uses that integral that I mentioned a few slides ago, where we have the derivative, the dt or the dx or whatever on top, and then the variable on the bottom. And that integrates to the natural log function. So this is what we end up with. We end up with negative b over m, which are just constants that are defined within the problem. And then we would pick up a t as we integrate. And then there would have to be some sort of constant assumed in the problem. Now, sometimes we can tell from a problem what that constant is, like it's an initial velocity or an initial position. But this is too complex of a problem to do that. We're going to have to kind of figure our way through what that c is. What we're going to do here is we want to get the v by itself. We want to get an expression for the velocity. That's our goal. And so to do that, we're going to use that trick that I mentioned where we take e to a natural log, and that gets rid of the natural log. So on both sides of the equation, we are going to take e to the expression. So e to the negative b over mt plus c, and e to the natural log of v. And again, the reason why we're doing that is because e to the natural log of v is just v. So it's a way of breaking it out of that natural log function. And then on the other side, we have e to this power, but you might remember that when you have addition within an exponent, it's really the same as multiplying two separate e, um, like e bases. So this would be e to a constant times e to the negative b over m. And since e to a constant is still just a constant, and we haven't really defined what that constant is, we're just going to keep calling it c. I know that's kind of a strange idea, but it's just something you have to kind of get used to when you're doing these sorts of problems. So now we'll use the initial conditions to figure out what that constant is. We will use t equals 0 and v sub 0 as our velocity. So we plug in 0 for t and we put in v sub 0 for v, and then we figure out that c would actually equal v sub 0. And so now we could write our final function as a function of time with v sub 0 as that constant times e to the negative b over mt. Now, what does this mean? What does this sort of function look like? Well, let's consider what happens as t gets really big. Okay, we know that when t is 0, the function has a value of v sub 0. But as t gets very large, you have e to a negative large number. That means really 1 over a very large number, meaning that this whole function gets closer and closer to 0. And so if we wanted to graph this to kind of visualize what's happening here, our velocity starts at this initial value, v sub 0, but it exponentially decreases towards 0. Let's look at one more example. Here we'll have an object that is falling, okay, so an object that has been dropped or released from rest, and there's again a resistant force opposing its motion. But in this case, that force would point upwards because the object is falling downwards. So I'm going to think a little bit about what the appropriate force diagram would be, and then see if we can represent the situation based on Newton's second law. So hopefully your force diagram, you're picturing mg pointing down and this BV pointing up, opposing the downward motion. And so your net force would be mg minus BV. And we'll make that same substitution where we change the a to a differential, dv over dt. And then we'll rearrange the variables, the symbols, so that all of the v's are together on the right-hand side and everything else is on the other side. Now, we need to keep that mg minus bv together. There's no way mathematically of adding or subtracting from both sides and still doing what we need to do. So think of that almost like it's got parentheses around it, and we end up with this expression. So we end up dividing by m and multiplying by dt and bringing that mg minus bv over to the other side. Now, the issue right now is, unlike the other situation where we had just dv over v and it was a fairly straightforward integral, we have dv over mg minus bv. And this mg is all filled with constants, so we don't need to worry about that. But this negative b in front of the v is a little bit of an issue. We have to have that as part of the derivative part on top in order for the integral to work. Again, when you're in calculus, you understand this a little bit better, but we're just going to have to kind of follow a pattern for right now. Basically, I need to multiply both sides of the equation by negative b so that the top is the derivative of the bottom. That's the pattern that has to sort of hold true in order for this integral to work. So I'm multiplying it by negative b because negative b would be the derivative of the bottom with respect to v. And if I do that on the right-hand side, I have to do it on the left-hand side as well. And then we would integrate both sides of the equation. And again, on the left, same sort of thing we got before, negative b over m times t plus a constant. And on the right, we get the natural log of everything on the bottom. Now, we're going to do that same trick where we take e to each side of the equation to get rid of the natural log. Again, there's kind of a strange thing with the constant, how it comes out of the exponent and goes in front of the e. I've switched sides because I want the v to be on the other side. Again, this is just a little bit of algebra. We can go through it in more detail if you need to. But I want to get an expression for v. That's my goal, again, is to determine a function for the velocity. So I'm going to go through and do some algebra here. I'm going to divide by b to get the v by itself. I'm also going to rearrange things, adding and subtracting to both sides as needed. Again, officially, it's a slightly different constant c because I divided by b, but again, don't worry too much about that. I know that's an odd idea, but we still haven't even found what that constant is, so it doesn't matter. We just need to recognize that there is a constant that we're going to need to find. All right, so let's go ahead and find that constant now. We can use the fact that this object was released from rest, so t is 0 when v is 0. So we can plug that into our equation. And then e to the 0 power would just be 1. So this is really 0 equals mg over b minus c. So c must also be mg over b. And so we can either write our equation by just replacing the c with that expression, or a lot of times it's factored out. Mg over b times this expression 1 minus e to the negative b over mt. Most important, I think, for this case, why I want to do this, is I want you to see sort of what these equations look like, so that if you do encounter a multiple choice question, maybe you can sort of recognize what the function looks like. But let's dig just a little bit deeper into what this equation is showing us. So let's imagine what happens as time passes and t gets large. As it did before, when t gets large, we are taking e to a very large but negative number. So it's like 1 over a very large number, meaning this whole part of the equation goes to 0. And so all we've got left is mg over b times 1, or mg over b. So what's happening here is that our velocity is approaching this value mg divided by b. And we call this the terminal speed. This function, when you graph it, it looks something like this, where it starts at a value of 0 velocity, and the object is going faster and faster and faster, but it does reach kind of an asymptotic value. It does reach a terminal value, what we call the terminal speed. Now you can see this in a less sophisticated way. We think more conceptually, but with just some basic formulas here. So rather than thinking about a as being a differential, let's just think about it as acceleration. Now initially, your velocity is 0 because this object was dropped. And that means that b times 0 is 0, and our equation would just be mg equals ma. Our acceleration is 9.8. But that means the object is accelerating. And so its velocity would be increasing immediately, and we would be subtracting a value from mg. And this amount that you're subtracting keeps on getting bigger and bigger, so the net force would keep on getting smaller and smaller. Eventually, that net force is going to be 0 at the point where mg and bv are the same value. And at that point, we would reach the terminal velocity. So we can find that terminal velocity a little bit more simply by just setting the net force equal to 0 and finding the value of v at that point.